The derivative and integral of e to the x. This may very well be your favorite lesson of the year. If you like your math to be on the easy side, then this may be your favorite lesson of the year. I'm going to jump right into these things. The short of it is, by the end of this lesson, you will know two new derivatives and integrals. One new derivative and one new integral. So first, the new derivative. If anyone ever asks you to take the derivative of e to the x, you tell them that it's e to the x. Fantastic. Then you need to memorize that, right? So make sure you make a flashcard for that one. What about the integral? What about the integral of e to the x dx? Well, given that the derivative of e to the x was e to the x, it seems reasonable that the integral of e to the x would also be e to the x plus c. And I suppose there's a sense in which this lesson could stop here, because that's the new material that you need to know. You need to know that the derivative of e to the x is e to the x, and that the integral of e to the x is e to the x plus c. What I'm intending to do with the rest of this video is give you just a couple of examples of each of them, sort of in action. Because the thing I do have to point out to you is that for as much as this derivative is true, we need to remember the product rule. We need to remember the quotient rule. And we need to remember the chain rule. We really need to remember the chain rule. Like, the chain rule is really, really, really important. So make sure you remember that. Regarding the integral, we need to remember that u substitution is still totally valid, is still there, and is still something that we need to know. So we're going to go through some examples of this now. Let's start with some derivative examples. So I could say, find the derivatives of the following functions. So I'm going to do a few of them. The first one, so what if I give you the function f of x is e to the x squared minus 3, right? So in some sense, this function is like e to the x, but it's e to the, not just x, e to the x squared minus 3. I hope you guys clearly see that this is a chain rule problem, the derivative of this. Well, the derivative of e to the something is supposed to be e to that something, so it will be e to the x squared minus 3 times, chain rule, times 2x. And so if I made this a little bit prettier, we'd be looking at 2x e to the x squared minus 3. And there's your derivative. Right? So note, we learned up above that the derivative of e to the x is e to the x. But that doesn't necessarily mean that every problem is going to see that you're going to see e to the x at the end of it. In fact, what it means is if you have e to the something, the derivative will always include e to that same something. Like, in some sense, the first step of taking any derivative of e to a power is to write e to the power again, and then probably remember the chain rule, right? So let's look at a second example of this, right? What if I had g of x equals e to the sine x? If you're watching at home, I'd recommend you pause this and write down this derivative on your own. So the derivative of this, well, the derivative of e to the anything is e to that same thing times the derivative of that thing, because of the chain rule. The derivative of this one is cosine x, and we can either leave the answer there, or we could move the cosine x to the front. To be honest, either one of these is fine by me. I suppose I'll go through a third. I don't want to do a lot of these examples because I really do want to keep this video short. What if I had a function, I did g last time, so what if I did the function h of x, which was e to the 2x over x cubed. Right, well, now this is a quotient rule problem. So when I do this derivative, we've got our rhyme. We do low and d high. The derivative of e to the 2x will be e to the 2x times chain rule times 2 minus high d low, square the bottom, and come at me, bro. And now I simplify this a bit. H prime of x is, let's see here, I can do 2x cubed e to the 2x minus 3x squared e to the 2x all over x to the 6th. And at this point I'll recognize there's an x squared here, x cubed here, x to the 6th here. I can cancel x squared out of all of those. So h prime of x will be 2x e to the 2x minus 3 e to the 2x all over x to the 4th. So h prime of x. And the last thing I can do is you can actually factor the top. I could factor out e to the 2x and have 2x minus 3 over x to the 4th. And that's the derivative. Just kind of want to point out, what if I asked you to find the x-coordinates of any horizontal tangents? I hope that you would remember that horizontal tangents happen when the derivative is equal to 0. So I would basically need to set the derivative that I just got equal to 0. But again, we've done this before. Hopefully remember that when you have a fraction equal to 0, it's just a matter of setting the numerator equal to 0. So you're just looking at where does e to the 2x equal 0, and then where does 2x minus 3 equal 0. Well, the one on the right is really easy. This is just x equals 3 halves. So there's one horizontal tangent. But what about this one? Right? Is there any value that would make this work? And one option is to sort of go the common sense route. Like, is there any power that you can raise e up to get 0? And understand that just in terms of common sense, no. The other option is that, based on what you guys saw in some of the review videos, this is an exponential form. We could change forms. We could say, oh, this is the same as saying the natural log of 0 equals 2x. But then hopefully you would remember that the natural log of 0 is undefined here. So this equation, has no solutions. So that's kind of all I'm going to say about the derivatives of e to the x. Just remember the product rule, the quotient rule, the chain rule, especially the chain rule. Oh my gosh, please remember the chain rule when you're doing this stuff. It's really, really important. I'm going to spend a minute or two doing an example or two of integrals involving e to the x. So for instance, what if I were to ask you, what is the integral of e to the 5x dx? Now remember, what we learned in the beginning of this lesson is that the integral of e to the x dx is e to the x plus c. But you guys should know about integrals. If you have something that looks different from something else, you cannot just do that integral. You can't just say, oh, e to the something is e to the something. It's e to the x alone. So if there is something else in here, understand, this is like being plugged into e to the x. So you're going to need to do a substitution here. U equals 5x. That means du is 5 dx. That means du over 5 equals dx. And so, sort of, plugging this stuff back into this problem, I now have the integral of e to the u times du over 5. That means we can pull out the 1/5. And now, this thing, that is the thing that we learned. That is the integral of e to the u. Du is e to the u plus c. So I have 1/5 e to the u plus c. And my last step is plugging u back in. 1/5 e to the 5x plus c. Right? And this can go further as well. We can have more complicated things. What if I had something like the integral of, let me try and think of something that's going to work out well here. The integral of 6e to the square root of x over the square root of x dx. I mean, this is really kind of a mess, but I hope you guys recognize when you see something in the power of e to the x, notice I just said in. This thing is basically being plugged into e to the x. So since it's being plugged into e to the x, that really should be a natural choice for our u. If I make my u the square root of x, that means my du is 1 over 2 root x dx. And we've talked about this specific problem before. If you want to get dx alone, you should just multiply both sides by the 2 root x. So if you multiply this side by 2 root x and this side by 2 root x, these will cancel. You'll end up with 2 root x du equals dx. And now I can plug that stuff into here. This is the integral of 6e to the u over. Now I could plug in u here, but I'm going to leave this as the square root of x, mostly because I know that my dx is going to turn into this. It's going to turn into 2 root x du, and I would really like that root x to be there to cancel out. Right? So now that I've done that, I have basically 12 times the integral of e to the u du. And again, I've now reduced this problem to just being, the integral of e to a single solitary variable. That means I can make this 12e to the u plus c. And then the final step is just plugging that u back in. 12e to the root x plus c. There are some more complicated problems in the homework tonight. If I get time later today, I'll make another video covering some of that stuff. But if you guys remember all of the review stuff, if you remember how to solve differential equations, if you remember how to find the equation of a tangent line, if you remember how to, take, for instance, take an integral with a number on the top and a number on the bottom. I said those backward, but that's okay. If you remember how to plug those numbers in, you may not need the third video. So if you've got time tonight, I would sort of recommend start the homework. Pick a couple random problems and try them out. If you're getting those, great. If you're not getting them, take a look at the third video. Like, go through some of those, maybe, fast forward around and see which problems you need to see. So I may see you in the next video, or I may see you in class. Have a good one.